everyone, this is my latest project. It's a VCO, it's a saw core oscillator, and then the saw core is converted to triangular and square wave with pulse width modulation. Here I have a lot of knobs and jacks. These 3 jacks, the bottom, these are the outputs for the saw, triangle and square wave, and the other things are the inputs. I will publish the schematic and the PCB on my Patreon, so consider subscribing there if you want to make this oscillator. connected all the three inputs to a mixer of the VCO, so I can choose the waveform I like. Now let's increase the modulation. See how the duty cycle changes. The triangle wave. And here is the saw wave. Now let's use the LFO to control the frequency modulation. You can combine different types of waveforms. The tuning is with these top two trimmers, and for the offset voltages you have to use these inside trimmers, and to set the offset voltages correctly you first start to measure the saw wave output, and now it's 0 millivolts because I have already adjusted it, but if I change it, you see how it changes. And also a good representation is if you plug the triangle wave to sound while you are adjusting this offset voltage, because if the offset voltage is non-zero, the triangle wave is distorted and it sounds more harsh. You see, when the offset voltage is 0, it sounds very mellow, and if I go to the other side, it also starts to sound harsh. And if you measure the pulse width modulation output, if I change the duty cycle, the offset voltage changes, but this is normal because if it's in the middle, it's 50-50 square wave and it's 0 DC. But if the square wave is it's not 50-50 duty cycle, it starts to be more on the positive or more on the negative side, so there is some offset voltage. When you have set the first trimmer, then you have to measure the triangle wave output, and you see now there is a DC offset and it should be 0. You can set this offset voltages to be 0 to remove the DC voltage offset, and it's not using capacitors, and the output of these oscillators is DC coupled. And this is nice because if you plug it through a AC coupling capacitor, it distorts the wave a little bit. This is the schematic for this VCO. These are the two parts. This is on one of the boards and this is on the other board. This is the generation of the raw saw wave. So this is the oscillator core, and then this part converts the raw saw wave into triangle and pulse width modulation. And here first, this is a summing op-amp which sums all the control voltages. There is a thermal compensation resistor here, and then this is like a bypass to compensate for the exponential curve of the transistors, because they go a little flat on the high frequencies, so the voltage should be a little bit more linear on higher voltages. The exponential curve of the transistors is too curved, so this straightens it a little bit with this trimmer to adjust it to match more closely to the 1 volt per octave transformation to a frequency. This transistor has a negative voltage on the emitter when you apply control voltage here. This makes so that there is current flowing from base to emitter, which creates a flow of current also here. So this transistor drains current from here, and which causes this op amp to output positive voltage, because this op amp tries to keep these voltage values the same. So if this voltage here is negative, it sends positive voltage here, because it wants to keep this to 0 volts. There is no connection here because this JFET is kept at minus 12 volts, which makes the source and the drain to be separated. This makes it charges this capacitor, because the voltage has nowhere to go apart from charging the capacitor. So it charges the capacitor and the voltage at the capacitor rises. This is the comparator, compares this voltage level with this signal here, and it reaches the value set by this voltage divider, which is like 2 volts and something, to a little bit more than 2 volts. Then this op amp switches from negative to positive voltage, and this voltage goes to this JFET, which is the JFET when you don't apply any voltage to the gate. The source and the drain are connected, but here is minus 12 volts constantly applied to the gate, so the JFET is open, so there is no connection here, and this capacitor charges. You see, this is basically the charging of the capacitor, and when the charging the capacitor reaches this value, this op amp sends a positive trigger here, and the JFET is for a split second made to conduct between the source and the drain, which drains the capacitor immediately. Exponential frequency modulation comes from here, and the linear frequency modulation comes from here, because this is bypassing the exponential conversion from the transistors. And this, if you apply voltage here, trigger signal, it acts like a sink, and the sink signal is applied here because this is the reference voltage for the comparator, and if the voltage value here changes, it will reset the phase of the saw wave. And this is through a capacitor, so actually the voltage won't change, but if you apply, for example, a positive trigger here, it will instantaneously change, so it will just reset the phase, but the saw wave won't reach a higher voltage. And then this raw saw wave is sent to the other board, and it first goes to this op amp, which amplifies it 4.7 times to match it to 10 volts peak to peak. So around 5 multiplied by 2 volts, that's 10 volts peak to peak. And then it's centered with this trimmer. This is directly the output for the raw saw wave. And then this raw saw wave is converted to triangle wave here. And this is done by first taking only the positive part. If we see only this part, it takes only this part of the saw wave. And this other thing first inverts the saw wave, and then only again takes the positive part of the saw wave. And when you combine these two things together, it creates a triangle on the top part, so on the positive part of the graph, which swings from 0 to 5 volts. And then this signal, here the op amp multiplies the signal 2 times, because this is from 0 to 5, so it's 5 volts peak to peak, and it should be 10 volts. So this multiplies it 2 times, and then this trimmer moves it down to center it. And this is why first you have to adjust the saw wave to be centered, because if it's not centered, this process will not work correctly. And let me show you. So if I change this here, you see now the triangle wave is distorted. So this is why you can use the triangle wave to check if you have adjusted this trimmer correctly. So if there is no DC voltage here, then the triangle wave will be fine. And then this part here converts the saw wave to pulse width modulation. This op-amp sums the inputs for the control voltage for the pulse width modulation from an LFO and from a potentiometer, and combines these two signals and sends it to this op-amp. And the voltage here, if it's for example 1.5 volts, this op-amp compares it to the saw wave, and when the voltage in the saw wave reaches 1.5 volts, the signal here flips to negative. Then when the saw wave again triggers and it rises above 1.5 volts, then this goes to positive again, and this creates the saw wave. And by changing the value of this potentiometer, you change the value which is sampled by this comparator, so you change the duty cycle of the square wave. So this is exactly the same schematic here, and these are the two boards. This is nice to fit in a Euro-Rec format, and I made it so that they stuck together on top of each other. These files will be available on my Patreon.